you can see what her talk is about. But Camila is a fourth-year Ph.D. candidate in the University of Arizona Geosciences. She's working with Hervé Rezeau, who's moved on to MIT, but she's continuing on with us. She came here with a Fulbright scholarship, and I understand that she's doing wonderfully well in her graduate program, and she was the recipient of the Lee Allison scholarship from us last year, this year, I guess. Was it 2 years ago? So she was gracious enough to agree to come and give a talk on her research, which is great. I think the more that we can get from that, the scholarship people that we award, that's wonderful. So come on up. Okay.
Hello, everyone. Can you hear me well? Okay. Well, thank you for coming. As Phil mentioned, I will talk about Filo del Sol today. It's a long title, but overall, I would like to show the ore characterization, spatial distribution, and the implications of that, the mineralization in the Filo del Sol, which is a copper, gold, and silver Porphyry-Epithermal deposit in the Central Andes. First of all, I would like to acknowledge all the different associations that have helped me throughout my PhD, such as Phil mentioned, Fulbright, SCG Foundation, AGS, NSF recently, and Vicuña for providing me with the data. So to start with, I would like to show the importance of Vicuña, which is the new emerging giant district in the Central Andes. So for a long time, there was a gap between the Maricunga, which is a world-class copper, gold, and silver belt, and El Indio. So let's see. Okay, here we go. So here we have El Indio, here we have Maricunga, and in between there was a gap for years. So a lot of people thought that that was barren, or there was not a lot of exploration over that region, which is because actually it's like really hard to get there. But recently they discovered this district which contains not only Filo del Sol, but Jose Maria, Lunahuasi, Los Helados on the Chilean side, and Caserones also on the Chilean side. So the overall importance is that Vicuña can contain copper of 13 million tons of resources measured and indicated, also 32 million ounces of gold, and 659 million ounces of silver. And Filo del Sol itself can contain 787 million tons of resources indicated and measured, plus inferred at 1.14 copper equivalent. So why is that important for Argentina and the region overall? Well, thinking about the top 5 commodities that Argentina produces, and this is data from 2023, we have that in first place, Argentina produces lithium. In second place, silver. Third place, gold. Fourth place, lead. And in fifth place, copper. So this is, as I mentioned, the annual production based on 2023 source. And nowadays, and this is data from 2024, we see that actually exploration is taking a lot of place in Argentina, where we can see that we have some different porphyry copper deposit systems such as Filo del Sol and Jose Maria, which is also part of the Vicuña district. And all of these different deposits are porphyry copper deposits. So then let's think. We do have a lot of exploration, but none of them are actually in production. So we as a geologist not only need to discover them, but also bring it into production. And one way of doing that is to transfer from resources into reserves. And we can help to that by increasing the geological assurance of the deposit. Sorry. Okay. But also, it will depend, of course, as you know, of different other factors such as the politics, environmental factors, geometallurgic. In this case, it's really important as well. And so, let's think, how can we help? Well, as I mentioned, by increasing this geological confidence, we need to go from essentially what we can log, which in this case it's high sulfidation, and it's really destroy and alter. This is like the first 300 meters or 200 at least. So we know through assays that we can get 0.74% of copper, almost 0.5 grams per ton of silver. But we actually need to understand how the metals are hosted there. So in this case, we need to know where copper, gold, and silver are. So I am showing an example over there where we have a silver sulfosalt and we have a pyrite with a copper-rich core. So we need to do a good ore characterization. And with that, I will present the main goals and objectives of my talk and part of my Ph.D. as well, which is essentially to characterize the ore textures and the metals distribution in the deposit. And the research question itself, it's where are copper, gold, and silver hosted? Also, to understand the processes that led into mineralization. And the question will be, which are the driving mechanisms that led into that for the enrichment of these metals? And finally, I will characterize the source of the mineralizing fluids. So, which are the different physical-chemical conditions of ore precipitation. But first of all, I will present Filo. So Filo, as I mentioned, is a copper, gold, and silver high sulfidation deposit, which is overprinting a copper-gold deposit. The age is around 15 MA. And here I have an schematic representation where we have the mineralization of the porphyry, copper, gold, and on top we can have disseminated gold. If we go slightly deeper, we can find the copper, gold, and silver veins. And if we move laterally towards a more distal area, we can find intermediate sulfidation, which is represented throughout different base metal mineralization. So in the case of Filo, this is completely overprinted, which means that we have the porphyry and its telescope due to the high sulfidation. Telescoping can be due to uplifting and erosion, or both. And to present a little bit of the geology, this is a simplified map where we can see that on pink we have the main host rock, which is Permo-Triassic igneous basement. Then on this color, which is brown, we have late Cretaceous volcanosedimentary rocks. And following the main trend, which is the main structural trend, which is northeast-southwest, we can see different mafic intrusions. Regarding the porphyries, which are Miocene, we see them on the southern area, which is called Tamberias. But we also know that they are mainly at depth in Aurora and in Bonita, which is this target towards the north. So I will mainly focus on Filo, Aurora, Refugio, and Bonita for my talk. And if we see this cross-section, pay attention, I will really re-emphasize this northeast-southwest cross-section throughout the talk. So this is a simplified cross-section I made with the drill hole data plus a little bit of interpretation. And we can see that, as I mentioned, we have the porphyries associated to them the magmatophreatic breccias over here. And also we have late magmatic hydrothermal breccias on pinkish, and on red we have the phreatomagmatic breccias. And so that's post-dating the host rock. Then we have an alteration map, and as a typical HS porphyry system, we have in the core a baggy silica on light blue, and then going to a more distal area, we have quartz alunite, quartz clays, which is mainly kaolinite, also sericitic in yellow, and then propylitic and subpropylitic. Looking at the same cross-section, we can see that we have some potassic in the bottom area of Aurora and Bonita, and some outcrops in the southern part, which is Tamberias, which I won't go deeper on that. And this is completely overprinted by the quartz clays and quartz alunite alteration. So just some examples of how these rocks look like. So I will show some examples from the porphyry area. So we have here some, this is one of the porphyry faces, which has potassic alteration, and we can see over there the K-feldspar with magnetite, secondary biotite, and EDM vein. The mineralization is mainly pyrite and copper sulfides. And then also another example, this is more from the phyllic halo. We have here that all the feldspars are completely altered, as you can see. And we have a molybdenite pyrite and quartz vein, which is cross-cut by a sulfide vein over here. So going into the epithermal system itself, we can see that we have a clear epithermal vein. In this case, we have 2 generations of pyrite over there. So over here, we have these different pyrite veins. We also have a lot of enargite, massive pyrite, and very important, here in this area, we have a lot of alunite as bags, which also contain pyrite and enargite. Very important and with a high participation in the system are the different brechas. In this case, this is a late hydrothermal breccia, where we can see that it has a cement of pyrite and enargite leuconite. And if we go towards the north, as I mentioned, we actually see some examples of intermediate sulfidation. So we see that we have on top, near the surface, a breccia, which is gypsum and barite cemented, and has sphalerite, chalcopyrite, pyrite, plus phalor, which is tennantite tetrahedrite. And towards the same area, but deeper, we can see some veinlets which contain galena, sphalerite, chalcopyrite, pyrite, and phalor, with some silver sulfosalts such as pearsite. But now let's think about how the minerals and, in this case, the metals are distributed. So this is the same cross-section with the drill hole data. In this case, it's copper. So we can see that it actually has a lot of copper, in some areas more than 1% of copper. But it's overall, I added the bottom of the oxidation, because we can clearly see that we have the oxide zone and what it's called the high-grade sulfide zone. So copper is hosted mainly in copper oxides in the top region, but we can also have a lot of different copper sulfides and copper sulfosalts, and we actually have copper in pyrite. Overall, regarding the content of copper, it's not extremely, let's say, important, but we can actually get up to 4% of copper in pyrite. So it's a lot, considering that pyrites widespread throughout the system. Now if we see the gold distribution, so in this region, throughout assays, we have very high grades also of gold, but this region is completely destroyed, so it was really hard to log and to determine how actually the gold was there. But we know so far that in this region, gold is present as native gold. It has been reported. I mainly found gold in pyrite, gold in enargite, and gold in copper sulfide. It's reported from the porphyry region. Then silver. So there is a high-grade zone of silver, which is called a manto zone. I won't go too deep on that, but we can actually find a lot of different silver sulfosalts, up to 75% weight of silver in Billingsleyite, and also we have cinnabar in that region. But in this region over here, if you see, we also get some high grades and more scattered areas with high grade of silver. And there, silver is in phalor, tennantite tetrahedrite, in pyrite, and in enargite. So if we just think about all the different mineralized zones, we get this diagram where we have a copper sulfide, mainly chalcopyrite region, which is associated to the porphyry over here. Then on top of that, we have a clear transition zone between the porphyry and the epithermal. And this region on top of that is dominated by enargite mainly. If we go laterally, we actually have enargite still, but it's cobellite dominant, and we have phalor that we didn't find in the center of Aurora in this high-rich enargite area. On top of that, we have the silver sulfosalts manto zone because of its tabular shape. We also have the copper oxide zone, and we have some gold, which we don't know again how is that distributed, if it's gold disseminated, maybe following the high-sulfidation model. And we have this region in Bonita mainly, which is base metal rich, gallinas, phallerite, and phalor. So from all these regions, pyrite is the most abundant mineral, and I will talk a little bit about how pyrite can help us. But first, why studying pyrite? Well, first of all, pyrite's really widespread throughout the system and in different stages of paragenesis. Pyrite has a simple stoichiometry, which makes things much easier in terms of the geochemistry. Pyrite is a refractory mineral and preserves distinctive chemical zoning. So here I am showing an image from Tanner et al., which studied El Indio. And we have a chemical zoning based on arsenic. So you will see here we have pretty rich areas with arsenic. Well, the good thing is that Filo del Sol pyrites are very arsenic poor. So you will see this just in this slide. Also, pyrite texture and morphology can show us different processes such as replacement and dissolution, or even recrystallization. And finally, the isotopic fractionation, if we want to do sulfur isotopes, they are pretty well established, so again, make pyrite easier to study and comparing to other studies. So now I will show some of the different pyrite textures we have seen in Filo del Sol. So we grouped them in 4 main groups. First, something that we call non-porous pyrite. So as we can see, it's like a crystalline pyrite. In this case, it's surrounded and pulsated by enargite. Then we have what we call porous pyrite. As you can see, the texture over there change. It's also called in the literature as spongy pyrite, and it's also associated with enargite. We have something that we call framboidal-like and framboidal-derived pyrite, and not framboidal as its definition, because it actually doesn't follow the strict definition for framboidal pyrite. And finally, we have a coliform pyrite type, which it's overgrowing a non-porous pyrite crystal and has this distinctive texture. So in this image, we also can see the different relationships throughout the pyrites. So here we have a porous pyrite vein, but we have some areas that still have some non-porous pyrite, and marcasite as well, which is growing in open spaces, which is the middle of the vein. So we have done some laser ablation mapping, which is in the square on red, and some spots also with laser ablation, which are on red as well. So what we obtain for these copper, gold, and silver metals is that if we see the copper distribution, this porous pyrite, it's really high in copper. We can get up to 4 weight percent in copper, as I mentioned. If we compare, of course, we do have some areas where we have lower values, and the marcasite that essentially doesn't have any copper. Then if we see silver, it's not completely correlative with copper, but still presents up to 1,000 ppm in this region which displays porosity, and also some higher values on the edges. And finally, gold. Well, gold we can get up to 10 ppm in pyrite, and again, mainly in this porous pyrite type as we see in the vein. Now if we analyze one of the other pyrite types, in this case the coliform one, let's see how the metals are distributed, and we see that copper again, it shows an oscillatory zoning, but this region over here, it's pretty copper depleted, and that's correlative with the non-porous pyrite. Silver, pretty similar distribution, although they are not completely correlative. But we see that this pyrite, the non-porous pyrite, is depleted in silver, and then we can reach up to 2 weight percent of silver in coliform pyrite. And finally, gold, we actually have 1 ppm of gold in the non-porous pyrite, and nothing, or well, just some areas with less gold, but it's, I would say, gold depleted. So if we see the overall distribution, this is a diagram with silver on the x-axis and gold on the y-axis. I made the normal score for all the different elements, trace elements in my pyrite. So I determined which are the boundaries to say, okay, this pyrite, it's gold rich or gold poor, just based on the normal score. So these are the different boundaries to set, different gold rich or gold poor areas. And here what we can see is that we actually have non-porous pyrites, which is on light blue. And most of them are silver and gold poor. If we go into the gold rich area, we have some non-pyrites, gold rich. But more importantly, we have in the gold and silver rich area that most of the porous pyrites and the rhomboidal pyrites have this enrichment in copper and gold and silver. And on the bottom part, we have a silver rich area but gold poor, which are the coliforms. So the main message here, we have clearly these two differences in the pyrites, but also if we see the regions where they come from, we see that the porous pyrites, gold and silver rich, are mainly from Aurora, whereas these pyrites here, coliform and non-porous, are from the Filo target. If now we see the same diagram, but instead of showing the areas, we show the domains. So I separate them in between Porphyry-Epithermal and transition zone. So we see that again, non-porous pyrite from the different environments are gold and silver poor. But we actually see that most of the porous pyrites in Aurora are from the transition zone between the porphyry and the epithermal. And here the coliform and part of the non-porous pyrites are from the epithermal itself. So just to show this was a lot of information. So just to show it graphically, how this looks like, well, we have a coliform pyrite over here. Sorry, I'm just in this target Filo, which is southern, and in Aurora we have on the transition zone the porous pyrite, which is essentially copper, gold, and silver rich, whereas the coliform is just gold and copper. I also add an example of non-porous. Besides, it's widespread throughout the system, but overall, non-porous pyrite from the porphyry is metal poor. So that was mainly about the different mineralization and metal distribution. Now let's think about which processes are leading that. So essentially, we think that this happens, this porosity is created throughout dissolution and reprecipitation processes. So in an initial stage, we have a primary pyrite, which is trace metal poor. So we have precipitation of non-porous pyrite with some microfractures or growth zones, internal zoning, or any internal channel that represents a weak area. In a second stage, we have coupled dissolution reprecipitation plus overgrowth, as you can see in the image. And that processes will affect mainly these weak areas. In a later stage, once it's more pervasive, we will have a complete or total dissolution and reprecipitation. So just by looking at different thin sections and different rocks, we actually see that that pattern also has been seen in some of the framboidal-like pyrites. And what we think is that if we have a seed, which can be any crystal of pyrite, and even we have seen it in enargite, we have nucleation of this porous pyrite. In a later stage, we can actually see agglomeration of those framboids, and that's how we'll get this, what is called a framboidal-like colony. So how can we explain then porosity? Well, porosity throughout different outers has been explained due to these microcrystals of pyrite is due to rapid crystal growth, where we have more nucleation than the actual crystal growth. And some authors, such as Ricard 2021, establish this process really happen in supersaturated fluids, where in this case, in this diagram, we have time. We have time over here. We have the logarithm of the activity of iron and H2S. So we see that we have this supersaturated fluid on these components. And once it reaches a certain point, which is called the critical supersaturation, what it happens is that it will occur the pyrite nucleation on this region. After that it's reached, actually all the fluid precipitates the content, and after that we have a regular pyrite crystal growth. So we think this is one of the leading process, and we can explain this with some also evidences in petrography. So here there is an image where we have a non-porous pyrite again. We have a very fine rim, which if you can see, it's like a brownish color. That is a very fine-grained porous pyrite. And after that, we see another area with non-porous pyrite, followed by another rim of porous pyrite. So we see a cyclicity on these processes. And essentially, in the trace metals distribution, and in this case I added silver, what we can see is that we have regions of silver poor, silver rich, silver poor, silver rich, regarding the pyrite type. So we associate this cyclicity due to metal-rich fluids, which we think they are associated mainly to the hydrothermal breccias. Now, just to support this idea, have we seen this in other minerals? And yes, we have seen that in enargite mainly, which is associated with pyrite. In this image, what we can see is a massive aggregate of enargite and leuconite. So they are polymorphous. And what we can see over here is this purplish color, it's enargite. The pinkish is leuconite. And if you see the texture, usually leuconite is more porous than the enargite. Well, that can happen. We actually don't know that completely, but maybe it's because leuconite has more antimony and it can be easily remobilized. Another example, it's an enargite vein that actually can recall all the different processes. So we see differences in textures throughout this vein, starting from a first generation of enargite, which is non-porous. Then we have another generation, which is porous. We have overgrowth of enargite, and again, some porosity. So what it's essentially showing is that we can evidence that dissolution, reprecipitation processes and the cyclicity in enargite as well. So just to show you a little bit of the trace metal distribution in enargite, this is not the exact same area I showed in the previous slide, but we did some laser ablation mapping, and what we saw is that actually most of the porous, it's the one that contain the metals, up to 10 ppm of gold. Although there are some regions on top that can even reach 100 ppm of gold. Silver follows the same pattern as gold, where the porosity in the porous area, we can find the highest silver grades. And so I won't go too much in detail on this. This is a really long paragenetic sequence trying to summarize the deposit. But overall, we can see that we have a porphyry stage copper-gold mineralization, and we have the epithermal itself, and we have a possible late stage which is associated to the supergene environment. So here I will focus on the epithermal and in particular on the main stage. So we have an early stage, main stage of copper, gold, and silver mineralization, and a final late stage with copper and silver. So we see here that we actually can find different cyclicity starting from the non-porous pyrite in the porphyry, then the epithermal, and then once we reach the mineralized event, we have this cyclicity between porous pyrite, rhomboidal pyrite, and then non-porous pyrite again. So I tried to talk a little bit about the processes, and now I will mention some of the physicochemical conditions. So regarding pH, well, we have a lot of alunite in the system. Much of the alunite is co-precipitating with this pyrite. And since we know alunite is stable between 2 and 4 of pH, we need very acidic conditions to form these pyrite types. So in this image, I just had an image from Hedenquist 2000, where we can see that alunite gives us that range of around 3 of pH, but also this is stable at less than 300 Celsius of temperature. So talking about temperature, again, presence of alunite can constrain the temperature, but also the presence of enargite and leuconite, if they are intergrowth, those are used as thermometers and can be between 200 and 330. And if now we think about the sulfidation state of the system, well, enargite itself represents a high sulfidation state, but cobalite it's even higher, and we have that in the outer areas of Aurora. And also the presence of tenantite, which is not in Aurora, it's on the outer areas, can show us a lower sulfidation state and probably less temperature. So just to show this diagram, which is initially from Barton and Skinner, but modified from Einaudi, we can see that there is a slight boundary between the enargite and the tenantite sulfidation state. But more important, to really understand the physicochemical conditions, we have done sulfur isotopes. And this might be a little bit complex to follow, but essentially sulfur isotopic compositions and the fractionation, it depends on temperature. So if we have less temperature, fractionation will increase. It also depends on the initial source of sulfur of the system. So it's like how much sulfur we started from, and the ratio between the reduces and oxidized species in the system. So overall, in this diagram, I would like to show the delta 34S. That's how we essentially measure sulfur isotopes. And in this case, I added silver on the y-axis. We can do that for copper or gold. I just took silver, because we actually can see different trends. And on this region over here, we have that if our delta 34S it's between 0 and -5, we assume this is from a magmatic source. So if now we go into this region, we start getting more negative values and we see like a trend, we actually think that can represent a cooling path. So some enargites are actually also showing a cooling path even with the pyrites. And we can model that by doing some thermodynamical models, and we obtain temperatures from 300 to 250 and an oxidized fluid. So that's the amount of the relative proportion of SO4. Finally, this manto zone, which is the one that contains the silver sulfosalts, actually show very negative values, very depleted in delta 34S. And this just can happen, or at least throughout thermodynamical models, at lower temperatures and due to highly oxidized fluids. So with that, I know it has been a lot of information, but I just want to summarize some of my ideas in this genetical model. So what we think, and throughout the different analyses on pyrite and the different mineral assemblages, is that we have the main porphyry center in Aurora. We still don't, we aren't sure if there is another porphyry center in Bonita, or if it's just the same for all the targets. What we definitely know is that we have this intermediate sulfidation assemblage, and that can be just due to cooling of these fluids, just due to solubility of the metals, or because we have another system in that region. Within Aurora and Filo itself, we know that Aurora can represent the feeder zone of the system due to its metal content and the characterization. And also we believe that the brechas, in particular the later hydrothermal brechas, have a very important participation in the mineralization of Filo del Sol, which are mainly occurring in this region over here, in the transition between the porphyry and the epithermal. I'm still understanding why that can be. I believe that that's just because we have a very intense potassic alteration, and then we have these quartz alunite, quartz clays overprinting that, so the change in alteration can be leading that change in porosity or ground preparation on the host rock. So most of the metal are over there, but it's widespread and we are still working on that. And related to Filo, Filo is really close to Aurora, but it also shows some specific characteristics, such as the enrichment in silver but not gold. So we also think that, well, it might be other fluid, or it just can be the same fluid that evolves into a silver-rich fluid but not gold, just due to solubility. And with that, some of the main takeaways is that copper, gold, and silver are hosted in different sulfosalts and sulfides, but it's also hosted in pyrite, and that it's really helpful to understand and to study the system. Coupled dissolution reprecipitation processes plus nucleation has played an important role in Aurora particularly. And this is driven by externally derived. That means that these breccia fluids, due to supersaturated fluids associated with the hydrothermal activity, are making Aurora the feeder zone and the higher participation of metals in that region. And finally, just sulfur isotopes can help us to understand oxidized fluids at specific temperatures, or highly oxidized fluids in a more shallower zone. Just to finish, the metal precipitation associated with the breccia events needs to occur at low pH due to alunite precipitation. And with that, thank you so much. I hope you enjoy the talk. Any questions? There is one over here.
Can you back up the slide one more before so we can talk about it?
Yes.
Does this work? Yeah, okay.
Maybe this one or that one?
That's a good one.
Okay.
First off, excellent presentation.
Thank you.
I have a lot of questions, but I won't hit all of them.
Okay.
But one, you just recently talked about the remobilization of metals, the late ones coming in, but you didn't really talk about how much effect from telescoping and downward sulfidation of the collapse of, say, the phyllic zone over the top of potassic and stripping of metals that usually occurs in the upper environments and copper, gold, and silver can get migrated downward during the telescoping of that system, precipitating on top of sulfides and sulfidizing things like bornite and chalcopyrite. So a lot of your photos are showing the mineralization associated with pyrite, but I wasn't sure if there had been effects that had happened on the primary chalcopyrite and bornite due to sulfidation in the telescoping process.
Well, thank you so much for your comment. Yeah, that's another option, thinking about that, like so I presented that is more like with a magmatic input, I would say, from the deepest areas to the more superficial areas. Telescoping indeed can help, but I particularly related this to the breccia activities just because most of the porous pyrites have been observed in those intervals, although it's widespread. And then regarding the copper sulfides, in the epithermal stage, copper sulfides are not enriched in silver and gold, at least not in Aurora and Filo. So my coworker is working in this northern area in Bonita and Refugio because the system is pretty long. So I am trying to correlate this, but I am mainly focused on the feeder zone. I don't know if answered the question. Thank you.
Any other questions?
Camila, I want to thank you for your very clear, wonderful slides. This is by far one of the best, visually one of the best presentations I've seen
Thank you.
in a long, long time. I am just absorbing this, and I apologize, I didn't have a chance to read the technical report before this, but it sounds so very complex, and I know that test work is in progress right now for metallurgical, but how do you grind, or how is this going to be recovered? I mean, this is great if we can make lemonade out of lemons and get some metals out of that pyrite, but how do you actually, I know that's not your field per se, but can you comment on the test work that's been done on segregation and processing of the various streams here? How would it be done?
Well, again, that's a great question. That's something that we always discuss with Hervé, and this is a very complex system. So far what I've known, what I've read from the technical report is that they aim to mine this and do lixiviation mainly. But I think like separating this in different geometallurgical domains will be really important. And yeah, I don't have more knowledge to answer like how specifically they will recover that, but yeah, I'm sure that it's lixiviation.
I could ask you a lot of questions, but I know it's not necessarily your field. When I see this, it's like I start screaming, PAG, a nightmare, from an environmental perspective. This seems really heavily pyritic, and yet it's a very dry environment. Do you have a feel for how this will react when you get waste rock dumps, or, you know, how will it react when it's exposed? It's already, like you called it, that outer zone is called a, what did you call it, a destruction zone? Or it's already, it's like a barren cap that's...
So you said on top on this region over here, or I don't know if I understand.
Well, I don't know if I can present myself on this, but from an environmental point of view, this is a really highly pyritic material. Oh. And you think about how is that going to be mined and managed to minimize impacts to the environment when it's so highly pyritic?
Well, so on this region, there is actually, in Aurora and Filo, there are like no outcrops. Like, it has actually been discovered mainly because of the alteration. So what you see on surface, and I have been there just once on Filo, it's really hard being there. It's just like 5,500 meters of altitude. So being there, it's terrible, first of all. But what it's, how can we observe that? It's just like the alteration zone. So you don't see actually pyrite or mineralization on surface, and that it's up to almost near the bottom of the oxidation. And then how will they extract that? I think it's open pit mining, but again, that's not my field to really go deeper on that.
So yeah, just more on that point there. Do you have a feel for what percentage of the gold resource is in oxide, something that might be cyanide leachable versus sulfide hosted gold demineralization?
Let me see. I'll actually go to the gold. So the highest gold grades are actually, okay, sorry, might take a while. But the highest gold grades are actually found in the high sulfide area. We do have a few on the oxide zone. See, we're getting close. Okay, we are there. So we still have like up to 0.6 ppm in this region. I cannot say how much because I haven't actually seen gold. It's just like when you are logging that, it's just like you see these black sulfides and black regions on the cores, but we assume gold is there, but you cannot see. And I think most of the gold will be in the central area over here, which is, again, this transition zone. And besides we have this native gold, it's, I would say, mainly in pyrite and enargite.
Okay, thank you. It does appear that looking at the plot there, there's quite a bit of gold within the oxide zone.
Yes.
So if, at least in the early years, if that was just open pit mining, that would not present an environmental issue from a acid generating standpoint. And there looks like quite a few tons that are contained within the oxide. So that probably plays into what Corey was concerned about there. And just one last question. I noticed that there's shows some reverse faulting basement over the top of some of the Cretaceous. Is there any post-mineral faulting out here?
I do believe that some of the northwest southeast faults are slightly later. The main trend, so the deposit itself, it's following the old structure, which is Okay. So if you see the deposit overall, this is the alteration follow this northeast-southwest trend. And those are like Permo-Triassic faults that have been reactivated. And the youngest structures are actually northwest-southeast. So the ones that are crossing.
Yeah, it looks like there's some visible offset on those. So I was wondering if that might have some implications for where there might be some yet hidden zones to explore if there's been some significant offset. It looks fairly minor, is that correct?
Sorry?
Yeah, the amount of post-mineral faulting and offset looks fairly minor.
Yeah, can be. Yeah, I think it hasn't been defined yet, the structural model for the deposit, to be honest. Nowadays, the geologists on the project are actually working on building the complete geological model with faults.
Is your entire resource, oh sorry, I can speak loud enough. Is your entire resource in Argentina?
No, it's part in Chile as well. Yes, it's actually a binational project.
I've got a microphone here too. Great presentation, Camila. Really enjoyed it. The slide you had with the pyrite and porous and non-porous pyrite, I really never really thought of it, but could you talk about what drives those cycles of going from non-porous to the porosity? And then you had that nice graph in there that showed it. What kind of drives those cycles? Yeah.
So to me, well, non-porous pyrite, you have different generations. You have the porphyry one, you have an epithermal one, well, several epithermal actually. But we see that from that, you have this dissolution reprecipitation process. And so once you reprecipitate, it's like easier to reprecipitate the pyrite as a porous pyrite. Just because if you have, in a short time, you have a supersaturated fluid that will just precipitate, nucleate, and then once the fluid gets stable, that you will get, again, crystal growth, like regular crystal growth, and have, again, the non-porous pyrite. So you will have essentially more time to crystallize and to growth. But when you have, that process is actually called burst nucleation because it's a really fast process. And it requires supersaturated fluids. So supersaturated in terms of the iron and H2S. And sorry, just to mention, so what I do think is that cyclicity is actually associated to different breccia pulses. That's why we see like several times. I've shown it like at least twice in one sample, but we actually have a lot of thin sections that we are still studying and thinking, well, this might be another generation. It's just like I have like 10 generations.
I have a question about the underlying model that's there that's with the different colors. Well,
so the last one?
No, that slide that you were on is just fine.
Oh.
But I'm just talking about basically the picture on the left.
Okay.
All of the slides that you're showing are longitudinally drawn, and I'm just wondering, was the geologic model built on section lines that were perpendicular to that longitudinal line, or it probably wasn't your work, right? I mean, it might have been someone else who built all of that, but I'm just wondering if you made a cross section perpendicular to your longitudinal one, would those units, the Vuggy silica and all the various other ones, do they have a shape like this, or are they just flat across there, or they, you know, what do they look like when you slice in another orientation? And I'm wondering too what it looks like in plan view as you move up and down it, you know, how that model was built, because sometimes when you're only looking at one orientation, you get
Yeah.
sometimes the wrong perception of things. So I was just curious about it.
No, that's a great question. I prefer, as you said, to see this northeast, southwest, just because I can see the different targets from north to south. But actually, for this deposit, there is a publication from Rezeau et al., which is, I think, 2023. And he shows different cross-sections which are east-west. So as you mentioned, yeah, you can see that it follows this same pattern. So you have these porphyry intrusions, magmatic hydrothermal breccia. So it correlates well from the north-south. I wanted to analyze the different targets. That's why I prefer the north-south. But yeah, that's correlative with different east-west sections.
Do the various alteration units, do the various units that are mapped here, do they follow, if you look at it in cross sections in the other orientation, do they wrap around like this? I'm just curious about that. Or are they, more or less flat, or do you see them looping around over the top?
Oh, okay.
That's what I
no,
was sort of
they
getting
are
at.
like rounding it. They are not like just flat.
Okay.
Yeah,
Right.
well, that's my impression, at least
All right.
with those sections.
Yeah.
Actually, if we look at geological, can you go to the geological map? Yeah, the first one, yeah. The geology. Yeah, from here, what we see, there are three major structural features that are visible on the surface and from your map. And the northwest, southeast faults plays the major role as far as to the mineralization. When we see from the shape of the
Yeah, so
from the ore. So what has been possibly expecting is to see if we make an east-west or perpendicular to the shape that we are now seeing here. If you can see, you see the distribution. If it varies, you see you can see the variation or the distribution of the different ore types. So you have the northwest, southeast, the northeast, and southwest. You have also the low angle fault as the northwest corner. So
yeah,
taking into consideration all these structural features, maybe the lithology and the structure could have played a major role to the distribution of these different ore types that you have been describing.
yeah, I think on that, like the other structures, the northwest, southeast, at least they don't seem to show like a control in the placement of the mineralization as the north, east, southwest. So essentially, if you see, here are the breccias, they are mainly following this trend, and even these mafic dikes follows that trend. But yeah, I mean, there might be like a structural control on the east-west side. I don't know.
Yeah.
We got one from online, so hang on. So to get back to it, okay. This is from Logan Hill. Are the trace metal contents in the pyrite in the zones with porous pyrite, where the highest concentrations occur, significant enough to impact resource estimates? If a meaningful fraction of the metals of interest are tied up in pyrite, I would think that would present a metallurgical challenge, which I guess someone else
Yes.
had already asked that.
Yeah, indeed.
Okay, it's a comment. Okay, so thank you, Camila, for your nice presentations. I have a couple of questions. How to explain the presence of the, look like that's the silver sulfosalt, look
Yes.
like following like a horizontal almost mantle, how to explain that?
Yes.
Maybe it's lithological control, I don't know.
Well, that's a good question. That's actually the second chapter of my PhD, the silver sulfosalts. We have been talking with the people that works actually in the deposit, and below that you can find some of the mafic intrusions. So you do have like a lithological control. Those are thought to be like the seal, like a seal in the system. So yeah, that in that term. I'm still studying and analyzing if that silver is supergene or if it's hypogene. I have done some sulfur isotopes, and actually those conditions can be reached either in supergene or hypogene due to vapors on the waning stage of the hydrothermal system. So yeah, I guess that initially I also thought it can be like a paleo surface representation, but it follows that table shape pretty clear.
Okay. So the second question, please. When I see your cross sections, looks like one of the, for like a Yanacocha system, you know, Yanacocha district is following, like you have a lot of deposits in the case of Yanacocha's northeast trending. And below, for sure, also there are porphyry systems in Yanacocha, but what I can see here, it's look like a polygenic system. Why is not showing also diatreme? There are no diatreme system like this one, because these are big districts, supposed to be showing maybe diatreme, or not necessarily.
So the question is?
If you have diatremes localized here or not, I don't know. Diatremes, brechas, ferromagmatic breccia like this one.
Oh, okay. So
most of them basically is post or post of similar. In the case of Yanacocha, post systems, post main systems, but in your case, I'm not sure if you have diatreme breccia like this one or ferromagmatic breccias.
So regarding the brechas, what it has been published and what it's known, so you have a big ferromagmatic breccia, but that it's early. It's earlier than the mineralization. And then you have what it's called by Rezeau, the late hydrothermal breccias, but with that name, you actually have phreatic breccias. So the ferromagmatic breccia, it's like the late, and to me, it's the one that it's associated to these different supersaturated events. But you also have these pyrite and enargite cemented breccia, which is not phreatic. So you have different breccia events. And those are mainly in Aurora and Filo, but you see some smaller intercepts in Refugio and Bonita.
So for sure there are breccias, many breccias. We are still missing to maybe place in your cross-section over here.
I tried to add those. In the thin section they are, in the cross section, sorry, they are.
Okay, thank you.
Yeah, let me see. Thank you.
Vice President for programs, and you have some award things to give to the speakers, but I forgot to bring them. But I promise I'll deliver to her.
Thanks.
Is it off? Okay, well, you can hear me anyway. So anyway, and then I'd like to bring attention to next month's talk, which is our own Dan Aiken.
Oh.
Yeah, really. Wait till you hear the talk before you, it's going to be something different. It's stromatolites and friends, earth niches or niches through time. So that's first Tuesday in December, so come on down. Thanks.